My dear students, let me welcome you all to a new edition of Physics. In this edition, we'll revise Unit 2. We'll try to answer some miscellaneous questions. Questions such as write the scientific term, write the scientific expression, make comparisons, explain, and so many other questions. So let's get started. Revision on Unit 2. Okay, first question. What is the photoelectric effect? We want you to define photoelectric effect. Okay, it is emission, it is ejection of electrons of some metals by light of certain frequency. Your attention to the word certain frequency. Once again, photoelectricity is the ejection of electrons of some metals, surface of some metals, by light of certain frequency. We've got another question. Why does blue light eject electrons? Blue light is capable of ejecting electrons from a certain photosensitive surface, whereas red light has no effect on that surface. Okay, there is something here you should mention. Of course, blue light has higher frequency. That is to say, it has more energy, yes, per photon. Each single photon, each blue photon has energy greater than the red photon. So, blue light has higher frequency. That's to say, it has more energy per photon. Another question, will bright blue light eject more electrons from a certain photosensitive surface than dim light of the same frequency? Okay, once again, will bright blue, so we've got bright blue and dim blue. What is the difference here? Both of them are blue, so they've got the same wavelength and frequency. But they differ in intensity, differ in the number of photons. Bright blue has many photons, much greater photons, okay? So will bright blue light eject more electrons from a certain photosensitive surface than dim light, okay, of the same frequency, dim light blue or dim blue light? Of course, yes, because bright blue light has more photons than dim blue light. Another question. In the photoelectric effect, does brightness or frequency determine the kinetic energy of the ejected electrons? So let me say the question again. In photoelectricity, does brightness or frequency, brightness of the incident light or frequency of the incident light, determine the kinetic energy of the ejected electrons? Of course, it is, yes, frequency. So frequency determines the kinetic energy, whereas brightness refers to intensity, determines the number of ejected electrons. Another question. Does the photoelectric effect support the particle model or the wave model of light? This is very important question. Let me say it again. Does the photoelectric effect support the particle model or the wave model of light? Of course, it supports the particle model. Yes, it supports the particle model. Another question, we want you to list the following photons in order of increasing energy. We'll start with 1, having the least, then we'll go in, yes, increasing energy. Radio, infrared, X-ray, visible and visible light, visible radiation, and ultraviolet. We want you to list them in an increasing energy. Which one, yes, of them has the lowest energy? The answer will be given right now. Okay, starting from the radiation having the least energy, it is radio, then infrared, then visible, then ultraviolet, and finally X-rays having the greatest energy. Another question. This is very important question in a photoelectric emission experiment. So we've got an experiment about photoelectricity. In a photoelectric emission experiment, a metal surface in an evacuated tube was illuminated with monochromatic light of frequency. Your attention, the light has frequency greater than the threshold frequency, the cutoff frequency. So the light is capable of ejecting electrons. So the surface was illuminated with monochromatic light of frequency greater than the threshold frequency for such a metal. If the experiment is repeated with light of the same wavelength, same frequency, but of twice the intensity, what effect will this have on the photon energy, the maximum kinetic energy of the photoelectrons, the work function of the metal, and finally the effect on the photoelectron current intensity? We'll take it one by one. Okay, first of all, what about the photon energy? It will not change, simply because it depends on the frequency. And we didn't change the frequency, we just changed the intensity. We used the same light, but having a greater intensity. So the photon energy is not changed. And what about the maximum kinetic energy? Also, it will not change. It depends only on the frequency of the incident light. We didn't change the frequency. So maximum kinetic energy of photoelectrons will not change. What about the work function? It will not change, simply because it will change if we replace the photosensitive surface. If we replace the metal, we worked on the same metal, so the work function of the metal will not change. And what about the last item, photoelectric current? It will be increased. It depends on the intensity. Okay, this was very important question. Another question, a metal surface is illuminated with monochromatic radiation. Monochromatic radiation means radiation having just one wavelength, whose frequency is greater than the threshold frequency, so it is capable of ejecting electrons. Explain how to increase the number of photoelectrons emitted per second, emitted from the surface. How to increase the maximum kinetic energy of the photoelectrons. To increase the number of the photoelectrons emitted, we should increase, we should increase what? Thank you very much. We should increase the intensity of the incident radiation. And to increase the kinetic energy, maximum kinetic energy of the photoelectrons, we should, increase the, I can hear you say it, increase the frequency. So the incident light is replaced by another light having higher frequency. Okay. Another question, compare between. We want you to make a comparison between the theoretical predictions of classical physics on photoelectric effect and the experimental results on the same effect. So we want you to compare between theoretical predictions of classical physics and the experimental results. Theoretical predictions. First, yes, prediction. There should not be a cutoff frequency. Actually, experiments show, yes, that there is a cutoff frequency. Okay. And what about the second point of difference? Yes, theoretical prediction, they include there should be a time lag for emission of electrons. Time lag means a time between the light or the radiation is shown on the surface and electrons are ejected. There should be time lag according to the predictions. Actually, as a matter of fact, experiments shows no time lag at all. No time lag for emission of electrons occurs, practically. Also, according to the theoretical prediction, kinetic energy of the photoelectrons ejected, yes, should not be proportional to the frequency, and it should be proportional to the intensity. Actually, kinetic energy, maximum kinetic energy is proportional, yes, to the frequency. It depends on the frequency of the incident radiation. Okay, and as I said, they expected kinetic energy, maximum kinetic energy, to depend on intensity, but actually it doesn't depend on intensity. So we've got a wonderful comparison between the theoretical predictions and the experimental results. And now we want you to write the mathematical relation that expresses. We want you to write the relation that expresses, that gives mass of a photon. What about the mass of a photon? Mass of a photon is given from the relation h nu over c squared. H nu is the energy of the photon, c is the speed of light in space. So you could write, yes, either h nu over c squared or E over c squared. This was about the expression that gives the mass of the photon. And what about the momentum of a photon? Momentum of a photon is given from the relation mc, m mass of the photon, c speed of light. So it is h nu over just c, not c squared, or it is E over c. Relation that gives kinetic energy of a photon. Kinetic energy of a photon, it is quite simple. It is h nu, of course, and it is equal to, nu can be replaced by c over lambda, so it is equal to hc over lambda. So kinetic energy of a photon is equal to h nu. And what about kinetic energy of an electron? It is half mv squared. It is equal to half mv squared. M is the mass of the electron, v is its velocity. And what about the relation that gives the wavelength of the wave that associates a moving particle? For example, a moving electron. We want you to give the relation that gives the wavelength of the wave that associates a moving particle. Yes, it is de Broglie equation, lambda equals h over mv. mv is momentum and is denoted by pl. So lambda equals h over pl. Lambda is the wavelength of the wave associating, yes, a moving particle. We want you to give the expression that gives wavelength of the characteristic line in X-ray spectrum. Okay. Of course, characteristic line energy is given by E2 minus E1, which is h nu. So the difference between the two levels equals h. Instead of mentioning or writing nu, we could write c over lambda. and of course the wavelength in this way will be equal to, yes, hc over the difference between the two energies of the two levels between which the electron is, yes, is moved. Expression for maximum kinetic energy with which an electron freed from a photosensitive surface. Okay, it is quite simple. We want the kinetic energy of, yes, a freed electron from a surface by light having, of course, the light should have frequency greater than the critical frequency. Yes, h nu minus EW is equal to EV. Let me say it again. h nu is the energy of the incident photon. EW is the work function. Yes, energy of each incident photon should be greater than the work function. And the difference, yes, is converted into maximum kinetic energy. And it is also equal to, yes, EV stopping. So we can say h nu minus EW is equal to maximum kinetic energy, and it is equal to E stopping times the stopping voltage. We want you to give the expression of the relation of Wien's displacement law. Wien's displacement law, the product of lambda maximum and absolute temperature is equal to constant. So we can say lambda maximum 1 over lambda maximum 2 is equal to, yes, absolute temperature 2 over the first absolute temperature, T2 over T1. Expression that gives the shortest wavelength in X-ray continuous spectrum. Yes, EV, the energy gained by the electron, bombarding electron, is converted completely into a photon having maximum energy, which is equal to h nu maximum. So we can say, yes, EV is equal to h. And instead of saying nu maximum, we can say C over lambda minimum. So the shortest wavelength lambda minimum equals hc over EV. E is the charge of an electron, V is the accelerating voltage. The number of positive holes in the n-type semiconductors. Relation that gives the number of positive holes in the n-type semiconductor. Okay, P equals Ni squared over N. Okay, N is equal to, or roughly equal to, the number of positive donors. So we can say P is equal to Ni squared over N positive D. Number of free electrons in the p-type semiconductors. Number of free electrons is the minority charge carriers. Okay, so P is equal to N negative A plus N, small n is the number of electrons. P is roughly equal to, or approximately equal to, the number of negative acceptors. So we can say the number of minority charge carriers, number of free electrons, is equal to Ni squared over P. Okay, so it is equal to Ni squared over N negative, yes, A, number of negative acceptors. What are the factors affecting? Another type of questions, we want you to mention the factors affecting certain quantity. What are the factors affecting the dominant color of the radiation emitted from a glowing black body? Of course, it depends on temperature of the black body, temperature of the object. What about the factors affecting kinetic energy of the electrons emitted from a certain photosensitive source? Yes, it depends on the frequency of the incident radiation, of the radiation incident on the metal. Okay, factors affecting mass of a photon. Actually, it depends on mass of the photon equals h nu over c squared. So it depends on the frequency of the photon. H Planck's constant, c is a constant, so it depends on the frequency. What are the factors affecting the voltage required, voltage needed to stop an electron freed from a photosensitive surface? Yes, freed by light having a frequency greater than the critical frequency. Of course, the factors, yes, are the frequency of the incident radiation incident on the metal. It depends on the frequency. What are the factors affecting the wavelength of the wave that associates a moving particle? De Broglie equation. We want the factors affecting the wavelength of the wave that associates a moving particle. Mass of the particle and velocity of the particle. So mass and velocity of the moving particle. Factors affecting line spectrum of X-rays. First, the factors are, or the factor is the kind of target used in the tube. So line spectrum of X-rays depends on the kind of target used in the tube. And as a matter of fact, the higher the atomic number of the target material, the shorter the wavelengths of the characteristic lines are. Let me say it again. The higher the atomic number of the target material, the shorter the wavelengths of the characteristic lines are. This means, it means the wavelengths of the characteristic line spectrum will, yes, decrease when the atomic number is increased. Factors affecting conductivity or resistivity of a semiconductor. Actually, it depends on two factors. Temperature of the semiconductor, conductivity increases as temperature rises, and addition of impurities. So the presence of impurities affect conductivity of a semiconductor. And what about the factors affecting the magnification power of an electron microscope? The potential difference between the anode and the cathode. The greater the potential difference, the greater the velocity of the electronic beam, and the smaller the wavelength of the wave that associates the motion of the electronic beam. So, as velocity increases, the wavelength of the wave associating the motion of the electron is decreased. And now we've got another type of questions. You are provided with two iron rods. So two iron rods are held in a fire. One glows dark red while the other is glowing bright orange. One glows dark red while the other is glowing bright orange. Which rod is hotter? Which rod is radiating more energy? Okay, the hotter rod is the one which is glowing bright orange. How did I know? It is Wien's displacement law. Wavelength decreases as temperature increases. So it is the one that is glowing with bright orange. And which one radiates more energy? It is the same one also. So the rod which is radiating more energy is the one which is glowing bright orange. Another type of questions: what happens when the temperature of a black body is raised with respect to the wavelength at which the intensity of radiation is a maximum. Okay, the wavelength, the maximum wavelength will be shortened, will be decreased. So the answer, the wavelength at which the intensity of radiation of the black body is a maximum decreases. This is the answer. Wavelength is decreased as temperature is increased. Veins displacement law. What happens when an electron and an atom falls from higher energy level, denoted by E2, to a lower energy level, denoted by E1? Of course, a photon is emitted having energy, which is the difference between E2 and E1. So the atom emits a photon having energy equals E2 minus E1, and it is equal to h nu. Simply because there is, yes, a principle called conservation of energy. Energy is conserved. When does, another type of question, when does the value of the intensity of the radiations of the black body tend to be equal to 0? When does the value of the intensity of the radiations of the black body tend to be equal to 0? This happens, yes, at very short wavelengths and very long wavelengths. The intensity of radiations of the black body tends to be 0 or to be equal to 0. Explain. Thermal remote sensing is used in criminology. Thermal remote sensing is used in criminology because the heat radiated by a person stays for a while in the place where the person exists, even after the person leaves the place. Mention an application or use of thermal remote sensing. Mention an application or use of thermal remote sensing. Yes, it can be used in detecting and imaging moving objects in the dark at night by night glasses. We call this night vision. Mapping or photographing the surface of the Earth. Compare between photoelectric effect and Compton effect. Okay, definition of photoelectric effect. Definition of photoelectric effect, it is emission of electrons from the surface of some metals when irradiated with electromagnetic radiation of sufficiently high frequency. And what about Compton effect? When a very high energy photon such as X-ray or gamma collides with a very loosely bound outer electron, such an electron is assumed to be free and at rest. What happens? The photon gives up only a part of its energy to the electron and scatters in a different direction, having a lower frequency. So this was about the definition of each one of them. In photoelectricity, the entire energy of the incident photon is absorbed by an electron, such that part of this energy is used by the electron to break away from the surface, and the rest shows up as kinetic energy of the electron. But in Compton effect, the incident photon gives up only, part of its energy to the electron. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.